Hello, hello, class. So let's continue with the sample problems under the topic refrigeration and liquefaction. This problem is from Ma'am Roe's handout. Okay, let's read the problem. A Carnot refrigerator requires 1.3 kilowatts per ton of refrigeration to maintain a region at a low temperature of negative 38 degrees Celsius. Determine the COP of the Carnot refrigerator, the higher temperature of the cycle, heat delivered, and COP of this device is used as a heat pump. Okay, the first thing that we will do is to draw and write the given of the problem. So we're given a Carnot refrigeration. The diagram that we can draw is this. Okay. So for example, this is our cold reservoir. We need a certain amount of work to drive the refrigerator to absorb heat from the cold reservoir and to dump heat to the higher temperature reservoir. Okay. And then we're given the work shaft is 1.3 kilowatts per ton of refrigeration. Refrigeration. Also, we're given the temperature of the cold temperature or refrigerated space, which is negative 38 degrees Celsius. Converting to Kelvin. So let's convert to Kelvin na 235.15 Kelvin. What we're being asked is for A, the COP of the refrigerator. B, temperature of the higher temperature, so that refers to TH. And then letter C, work shaft if, no, heat delivered, and COP if this device is used as a heat pump. Okay. Okay, not the work shaft, but rather if heat delivered, that's QH. Okay, let's correct this to QH. QH and COP if heat heat pump. Okay, heat pump. All right. Before we proceed with the problem, let's define first what's a ton of refrigeration. Okay. A ton of refrigeration is actually, so 1 ton of refrigeration is equal to 12,000 BTU per hour. Without this information, we cannot solve the problem. Please remember that a ton of refrigeration is 12,000 BTU per hour. We write this formula for the COP of a Carnot refrigeration cycle. Okay, it's QC over work shaft. Okay, since wala naman pump sa Carnot, so QC over work shaft, and that is 12,000. Okay. So this ton of refrigeration is actually our QC. Okay. refers to the QC, or the heat absorbed from the cold temperature reservoir. Therefore, we have the values for QC and work shaft. We only need dimensional analysis. We write that 12,000 BTU per hour multiplied by 1 hour is 60 seconds, or 60 minutes. 60 minutes times the conversion of 3 point 3.517. So conversion factor, kilowatt per minute is 200 BTU per hour. Let me check. Let me check the conversion. BTU per minute. This is BTU per minute. Okay, so it's just a conversion factor over the WS, or work shaft. So this the entire term. Okay, let me just put it this way. Work shaft, which is 1.3 kilowatts. Oops. So let's see. This would cancel. 1 hour is 60 minutes. This would cancel. Okay, what else? 3.517 kilowatt. Sorry. So this is wrong because kilowatt is already in kilojoules per second. So let me, yan. So yan lang. Okay? So the conversion is, or rather the conversion factor is 3.517 kilowatts is to 200 BTU per minute. Okay? So therefore, the minute would cancel and only kilowatt will um, remain. We also cancel that. COP is dimensionless. And the answer is 2.7 for letter A. Letter B, we're being asked for TH. So we use the formula of COP in terms of temperatures. Okay? In terms of temperature. So we isolate TH, TC over COP plus TC. TC is given. COP, we already know that. So TH is, solving for TH, this is just 322. 322 Kelvin. Right? And finally, letter C. Okay, letter C, we're being asked for the QH and COP of the heat pump. So what if reverse? Okay, this is a heat, I mean, not reverse, still the same flow, but the valuable product is QH. My valuable heat is QH. Okay, as a heat pump. So we're being asked for QH and COP. The work shaft is actually just QH minus QC. So we know QS, we know QC, which is the ton of refrigeration. And then the work shaft is given. So let's solve for QH. So rearranging QH is just work shaft plus QC. Okay. And this is equal to 1.3 kilowatt plus so we don't know QC in terms of, so this part right here, okay, this part, solve for this part. All right. So if we solve this in its own, the value is, without dividing by work shaft, QC is equal to 3.517 kilowatt. Okay, so that's 3.517 kilowatt. Let me double check using calculator. 12,000 times 0.517 divided by 60 divided by 200. Yeah, 3.517. And the answer is 4.817 kilowatt. Or in the answer key, it's 281 kilojoules per minute. So the same, just in the unit of minutes. How about the COP of a heat pump? So the formula for the COP of the heat pump is QH over work shaft. Again, the difference is because the value of our desired output is QH, whereas in refrigeration, our desired output is QC. Okay, so I hope that's clear. And that is 4.817 kilowatts over 1.3 kilowatt, given yun. So that's 3.7. That's the COP. Okay? I hope this is clear. So now we proceed with the next problem on vapor compression cycle. A refrigerated space is maintained at -20 degrees and cooling water is available at 21 degrees Celsius. Refrigeration capacity is 120,000 kilojoules per hour. The evaporator and condenser are of sufficient size that a 5-degree minimum temperature difference for heat transfer can be realized in each. The refrigerant is tetrafluoroethane or R-134A, for which the data are given. What is the value of the COP? So this symbol here refers to the COP of a Carnot refrigerator. Calculate the COP and mass flow rate for a vapor compression cycle if the compression efficiency is zero point 0.8. So let's draw the diagram. If it's a vapor compression cycle, hindi sinabi if um, whether ordinary or standard. Let's assume na it's uh, in this step there's a throttle valve. So which type of vapor compression is that? Ordinary or standard? So that's an ordinary vapor compression cycle. And then, what else? So evaporator, compressor, condenser, throttle valve. Drawing the yes diagram, it should look like this. Then what else is given? So we're given the refrigerated space is -20 degrees. So let's write it as -20 degrees Celsius, and then the cooling water is available. So that is the condenser. Uh, at the condenser, 21 degrees Celsius. Refrigeration capacity is 120,000 kilojoules per hour. So that's QC, kilojoules per hour. And the evaporator and condenser are of sufficient size that a 5-degree minimum temperature difference for heat transfer can be realized each. And so therefore, we can write that T evap or temperature in the evaporator is, so it has to be, if the delta T is 5 degrees, then the temperature in the evaporator should be negative 25 degrees. Okay? And the temperature in the condenser should be what? Uh, 26 or 16. So dapat 26 degrees Celsius. So if we're given yung mismong evaporator and condenser temperature, we use this in the calculation of the COP for a Carnot refrigerator. And then we're given that the refrigerant is R1-34A or tetrafluoroethane. We're being asked for the COP of a Carnot operating at between these two temperatures, Carnot refrigeration cycle, and the COP of a vapor compression cycle, and the mass flow rate of that vapor compression cycle if the compressor efficiency is zero point 0.8. Okay, so let's solve the problem. The first question is the COP of a Carnot um, refrigeration cycle. So the formula is TC over T TH minus TC. So uh, TC is this one. Use the evaporator temperature, negative 25 plus 273.15 over the difference between the two, this one and this one. That is TH 26 minus negative 25. And you will get 4.87. Okay, so that's the answer for letter A. And for letter B, um, we are looking for the COP and mass flow rate of a vapor compression, an ordinary vapor compression cycle. So we look at state, let's begin at state 2, which is before the entry to the compressor. It's uh, purely vapor state. Okay, so let's at state, so at point 2, it's saturated, high saturated vapor. So we use the table. So from the table, saturated properties of um, tetrafluoroethane in SI units. So the temperature, by the way, we first should identify what is the temperature at point 2. So that's the evaporator, it's negative 25. So the temperature is negative 25 degrees Celsius. So that's T1 equal to T2. Okay? So let's check the table. Negative 25. The enthalpy is, for the vapor, it's 383.45 kilojoules per kilogram. So let's write that. Okay, from table at, we'll get H2 383. Oops. 383.45 kilojoules per kilogram. And then S2, same from the table, read the value. Okay, it's 1.746 kilojoules per kilogram Kelvin. The next step is at point, what else do we know? Let's try point 4, which is, this is subcooled. Subcooled. So let's keep point 4, or not, sorry, correction, not subcooled, but saturated liquid. Okay, so correction, we're not outside the saturated curve, so we're on the saturated curve, and to be exact, the saturated liquid part. So it's completely saturated liquid. So from the table at T4, tama ba? T4, T4 equal to the temperature in the condenser. That's 26 degrees Celsius. Okay, 26 degrees Celsius. Um, so let's check the table. 26 degrees Celsius. Alright, so H4 is 235.7, and uh S, how about, okay, S26, let me highlight that. 235.97. So that's, and S4 for liquid is 1.125. 1.125. Okay. So we can try to we can look at point 3. Point 3. Let's look at point 3. If we assume isentropic expansion, assume isentropic. So, by the way, before that, point 3, it's superheated. Okay, the state is superheated, tetrafluoroethane. So, next we assume isentropic compression. Okay, isentropic compression. Isentropic compression. Therefore, if isentropic compression S2, S3 prime equal to S2, right? S3 prime equal to S2, and that is equal to the values sa taas, 1.746. Okay? Um, so the next step is use the pH diagram since we're dealing with superheated tetrafluoroethane. Let me show that diagram. So use this diagram, okay, to read the state of um, tetrafluoro, I mean the entropy, not the enthalpy of tetrafluoroethane using the enthalpy value. Okay. But we don't know the pressure. Okay? We don't know the pressure at uh, point 3. So what do we know? How can we know the pressure? So remember, mm, so before we can use that diagram, the pH diagram, to read H3 prime, we need two properties. So one is entropy, and then since in the diagram, the y-axis is pressure, so we need to find the pressure. At the moment, we don't know the pressure, but we know that this line is an isobar. Therefore, P4 equal to P3 prime. Okay, P4 equal to P3 prime. And uh, during step 4, we should have read in the saturated property table, okay, yung P4. So remember, we just need one, we just need one property which is, oops, nawala. Okay, let me pause and find. Okay, so we need one property in the saturated table, so that's 26 degrees Celsius, and automatically ito, pressure is 1 bar, 6.854. And that is our P4, 6.854 bars. Okay, bars. Therefore, from the oops, figure, pH diagram, okay, at pressure, P3 prime equal to P4 equal to 6, 6.854 bars, okay, read from the diagram, okay, so I'll just let you read from the diagram using the pressure and the entropy to get the enthalpy. And you will find that the enthalpy is about um, H3 prime is about medyo exact na tong value na to kasi sa ibang table to kinuha. 421.97. So therefore, if we want delta HS, so that's H3 prime minus H2, that is 421.97 minus H2, 383.45, it's 38.52. Using the compressor efficiency, we can find uh, the actual H3. Okay, we can find the actual H3. But let's just, so this or the actual H, the H3 minus H2, okay, is equal to delta HS over efficiency of the compressor. So remember, the efficiency of the compressor, if it's a work requiring device, mas maliit yung delta HS. Okay, so just rearrange. So we will get 38.52 divided by 0.8. The answer is 48.15 kilojoules per kilogram. Okay, and then the next step is to find H1. But since so where's H1? H1 is here inside the saturated curve. But since this is a throttle valve, so this is isentalpic, H1 is equal to H4. So it's a saturated R134A, but step 1 to 4 is isentalpic. Okay, isentalpic. Due to the throttling process, therefore H1 equal to H4 equal to, what's the value? Let me go back to H4, 2357. 235.97. Okay, so now that we have all the H's, remember that our uh, equation for the COP of a ordinary vapor compression cycle is H2 minus H4 minus H4 divided by H3 minus H2. Okay, so we derived this during our class. Um, so just plug in all the values. You will get 3.06. Yeah, so that's the COP. How about the mass flow rate? So the mass flow rate is simply a mass flow rate of the refrigerant is just the heat over delta H. So we know that QC is given 120,000 kilojoules per. Let me go back to that. Kilojoules per hour. And then H2 minus H4. So this is H2 minus H4. So that's 383.45 minus 235.97. And the unit is kilojoules per kilogram. So our mass flow rate is in kilogram per hour, and the answer is 814 kilogram per hour. Okay? Okay, so this ends the problem. Alright? Okay, let's solve this problem on absorption refrigeration. But before that, let me paste the drawings. Okay, so we're given a reversible absorption refrigerator. Let me drink first. Consists of a reversible heat engine and reversible refrigerator. So reversible heat engine, reversible refrigerator. The system removes heat from a cold space at negative 10 degrees. So that's here. At a rate of 22 kilowatts, the refrigerator operates in an environment at 25 degrees Celsius. So that's TS. If the heat is supplied to the cycle by condensing saturated steam at 200 degrees, determine the rate at which the steam condenses and the power input to the reversible refrigerator. Okay, let's write the given. Huh? Okay. I accidentally click a button. I don't know what button was that, but I'm not on mute. Okay, given is uh TC. My TC is, so that's right here. TC is negative 10 degrees Celsius. Uh, Rate of 22 kilowatts. QC, okay, that's here. Uh, QC equal to QL equal to 22 kilowatts. And then the refrigerator operates in an environment TS 25 degrees Celsius. Heat is supplied at 200 degrees. That's TH 200 degrees Celsius. Required is rate at which the steam condenses. So the mass flow rate of steam, and also power input by W, this one, power input to the reversible refrigerator. Alright. Uh, so the first thing that we can do is uh, how to solve for the mass flow rate. So the mass flow rate of the steam would be equal to QH over delta H. Okay, that's QH over delta H. So if we're talking about steam, it's delta H of evaporation. Evap, right? This is something that we can obtain from the steam table. So our remaining unknown would be QH. So how can we solve for QH? We're given all the temperatures. We're given all the temperatures. We're given QC. And the COP formula for a completely reversible absorption refrigeration cycle is QL or QC. So that's referring to the same, is equal to 1 minus TS over TH divided by TC over TS minus TC. Right. So we're given this one, we're looking for QH, but let's solve for the COP by plugging in all of the temperatures. So that's 1 minus 25 plus 270.15 divided by 200 plus 273.15. Okay, and then TC is negative 10 plus 273.15 divided by 25 minus negative 10. Okay? We will get COP equal to 2.78. With that, we can solve for QH. So QH is just QL over COP. And this is 22 kilowatts given divided by 2.78. That gives us 7.913 kilowatts. Okay? So now we can use this formula to solve for the mass flow rate of the steam. Oops. QH is 7.913 kilojoules per second over, so by the way, delta H of evaporation is 1939 from the steam table at, so from the steam table, from ST at T equal to 200 degrees Celsius, delta H evaporation is, hold on, no, not negative, 1939.7 kilojoules per kilogram. Again, this is the difference between the liquid and vapor at 200 degrees Celsius saturated properties. Okay? So I will write that here. Our unit is kilograms per second. So the value is 0.00408 kilojoules per kilogram per second. Okay? Letter B, we're being asked for work. The work. Okay, so how can we solve for the work? So we can use the equation for the COP of the refrigerator. Okay, so we need work. So the COP of a refrigerator is what? It's QC or QL over work shaft, right? Um, but this time it's not due to shaft work, so let's remove the S. Okay. And this is equal to 1 TS over TC minus 1. Oops. Erase, erase, erase. This is the reciprocal. The formula is TC over TH. So let's just begin with the formula. TC over TH minus TC. Correct? Okay, so if we want to solve for work, it's simply QL over TC. So this is TH minus TC. Okay. So let's try that. QL is 22 kilowatts. TH is so the value is TS. Okay, so for TS, not TH, that is 200. So please take note of that. How can I erase this? Hold on lang. I will erase the TH. Sige na nga. Ano ba yan? Ayaw na. Erase na lang ulit. Okay. So that's TC over TS minus TC. So that's TS minus TC. Okay na, nakuha ba? So we're using the variables, the parameter assignment for this problem. And so we're using TS instead of TH kasi yung TH dito is 200, but we're just focusing on the ref, and our hot reservoir is the surrounding. Okay? Kuha ba? And that value is 25. Okay, but before that, let me go back to ito. Basically, ito yung formula na ginagamit ko. Ito pala, itong nasa ilalim. Ito, for work. Okay. So, in terms of absorption, refrigeration na uh, temperatures. So, TS is 25 minus TC is 10, right? 25 minus 10. 25 minus negative 10 over negative 10 plus 273.15. And the value is 2.93 kilowatts. Okay, so we're done with this problem. Let's move to the next problem on absorption refrigeration. Okay, so this is the next problem. Let's solve first letter A, an absorption refrigeration system that receives heat from a source at 130 degrees Celsius and maintains the refrigerated space at -5 is claimed to have a COP of 2. If the environment temperature is 27 degrees, how can this claim be valid? Justify your answer. So letter A first. Um, given we are given the temperatures, TH is 130 degrees Celsius, TC is -5 degrees Celsius, and TS is 27 degrees Celsius. The claim COP is 2. So just the required is whether this claim is true. Okay, that's right. Is claim true? Solution. We can do this by calculating for the COP of completely reversible absorption refrigeration and comparing it with with the claim COP, because the reversible absorption refrigeration will give us the highest COP possible. So if the reversible COP is higher than this value, then this claim is valid. Okay? So let's use the formula for the COP of a completely reversible um, absorption refrigeration. TC over TS minus TC. Plug in, plug in all the values and convert to Kelvin. You will get 2.14. So this is letter A. 2.14. Since this is greater than 2, therefore claim is valid. Letter B, so we're given pH is equal to 130 degrees Celsius. QH is equal to 5, di ko ba nabasa? Heat is supplied to an absorption refrigeration system from a geothermal well at 130 degrees Celsius at a rate of 5 times 10 to the 5 kilojoules per hour. The environment is at 25 degrees Celsius and the refrigerated space is maintained at negative 30 degrees Celsius. Determine the maximum rate at which the system can remove heat from the refrigerated space. Okay, so given, yan, pH is 130 degrees. QH is 5 times 10 to the 5 per hour. TS is 25 degrees Celsius. 25 degrees Celsius. TC is negative 30 degrees Celsius. Um, okay. So, ang tanong ay required, what is the maximum, determine the maximum rate at which the system can remove heat from the refrigerated space. So, that's QL. QL. So, we want to solve for QL. We don't know um ayun, yun lang naman ang unknown kasi COP, if we write COP, the equation, so I'll not write it again. This equation right here is, can I just copy paste? I'll just copy paste. Oops, hindi na copy paste. Anyway, just refer to that. And that value is, calculate COP, you'll get 1.151421. Okay. And that COP, kasi we're looking at maximum rate, so we can assume that completely reversible refrigeration, absorption refrigeration, that's why we can calculate the COP. This is reversible absorption refrigeration formula, diba? So we calculated that COP for that, and COP is QL over QH. Since we're given assumptions, reversible cycle. So we're given QH. Just solve for QL, which is COP times QH. So plugging in the values, you'll get 5.75 times 10. Well, i-write na rin natin. Sige. 1.51421 times 5 times 10 to the 5. And that is 5.75 kilojoules per hour. Okay? So, ang hint is pag sinabi maximum QL kasi this is so maximum, may hint na yon na reversible yung process. Okay? Alright, so let's end the video right here. Let's just continue to the next video, which is sample problems for thermodynamic analysis.